Morning, guys. How you doing? Any questions, comments, etc. before we get started today? All right. Let me know anything that crosses your minds while we're working today. We've been in Chapter 5 looking at momentum and collisions. On Monday we also added impulse to that list of definitions we've been using. Impulse just meaning change in momentum. To kind of continue on from that real quick, I want to give you guys a very quick practice problem to work on your own or amongst yourselves. And I'll just give you a couple of minutes to see what you notice and come up with in terms of an answer. We're going to apply all the information so far to baseball, because what is baseball but repeatedly trying to cause a collision between the bat and the ball? We are going to have someone pitch a 145-gram ball at 45.7 meters per second forward. Babe Ruth is then going, I believe these numbers are actually converted from this man's actual history, is going to strike the ball with the bat, and it is going to turn around and be moving at 69.4 meters per second in the opposite direction. The ball and the bat are in contact for 0.71 milliseconds. Collisions don't tend to last very long. All this information given, I would like you guys to tell me first, what is the impulse of the baseball itself, and likewise, how much force does the bat have to exert on the ball to cause that impulse in this amount of time? Give it a couple minutes, and we'll see what you guys come up with. What do you guys think?
impulse of the ball after it was thrown was 6.48 J. J equals 6.48.
Good guess, almost. I think I'm envisioning a specific wrinkle, and I'm going to kind of demonstrate what I mean. Given that we know the ball's mass and both its initial and final velocities, we can find its impulse by just comparing the two speeds together. You could either find the two momenta and subtract them, or you could...
Oh, it was asking what's the ball's impulse, like, in total, not
yes.
from when it was pitched.
Oh, yes, sorry. Impulse from impact, with the bat. Sorry. I didn't make that clear. Yeah, I want to know the impulse from Babe Ruth hitting it with the bat. Sorry. Yeah, what you found sounds correct if it's the impulse of just pitching it from rest. So, you answered that question correctly, just not this one. Apologies, yes, I would like to know the impulse of the ball when being struck by the bat, which means that we need to note its change in velocity upon being struck by the bat. It is initially moving at 44.7 meters per second forward, and then is hit to 69.4 meters per second backward. Those are two different directions. So if you just put those two numbers here and they had the same sign on them, which is to say that you end up subtracting the two numbers, then your work won't work out completely right because those two vectors point in opposite directions. This ball has a pretty big impulse because it goes from very fast forward to stopped and then very fast backwards. That is a very big change in velocity. If you just did this, put in two positive numbers, you'd only get a delta V of about 25, when in reality the delta V is supposed to be about 115 because the velocities have opposite signs. If the 44 is forward and the 69.4 is backward, then I would put a negative sign on the 69.4. So that's a negative minus something. That's going to give you a big negative rather than a small positive. You could reverse the two, in which case you leave this positive, make that negative, and then you're subtracting a negative, and then you just get a big positive answer instead. But one way or another, you have to note the two velocities point in opposite directions before you put them into the F minus initial. The other kicker here is, are you going to put in 145 grams? No, you want kilograms. And that should give us an impulse, specifically on impact with the bat, of negative 16.5, etc. Remember what the units are for impulse?
Kilograms, meters per second.
Very good. Same as momentum. And you could get a positive number if you just decided that the two initial vectors had opposite signs on them. As long as they have opposite signs, it doesn't matter which one you say is forward, as long as you're consistent. And then you would get this number, just the sign just depends on which direction you consider negative. Questions on finding this? All right, now that we have that impulse, we can use it to figure out how much force the bat exerts on the ball. So take that number, plug it in for J, equals F times the time that the ball and the bat are in contact with one another. That 0.71 is in milliseconds. How many seconds would that be? Yep, 1,000th of what it already was. So that's 1,000 times smaller. Collisions do not last very long. And if you convert that right, I'm going to round a little bit. That should give you about 23,300 newtons. which is about 5,000 pounds of force. Impressive. I will note though, I will point out, that is not this person's lifting potential or his punching force. That is the force he can output with the assistance of a baseball bat. Turns out most sports, if they involve some sort of a tool like a bat or a racket or a golf club, what you're doing with that is you are using the tool as a lever arm and utilizing torque to increase your force output. So with a baseball bat, Babe Ruth could hit something with a force of 5,000 pounds, but he could not lift 5,000 pounds. Does that make sense? Torque is actually going to be something we talk about, if not next week, then the week after that. So I promise I'll re-explain that when it comes up. Needless to say, though, it is still impressive. It's a lot of force, and it's often why baseballs that get launched over the stands often, aren't always in one piece. Sometimes they shatter. Sometimes the skin peels off. There's a lot of force involved in baseball, as it turns out. And it turns out pretty much all sports do a similar thing. They're just applications of torque, as long as you're, swinging a stick at something. Questions? All right. So, that's just a quick refresher on impulse. Now, we're going to be spending most of our time on today. Oh man, the arrow's got moved. We've been looking at how momentum behaves in a collision. And the convenient thing about momentum is, no matter what type of collision you're having, be it a normal collision, be it an explosion, be it any other subtype of collision, momentum is always conserved because it has no other form it can occupy. There's no subtypes of momentum, it's just momentum, as we've discussed. So no matter what's going on, total momentum initial will always equal total momentum final. This is consistent. That said, there are different types of collisions. We've already described explosions as one subtype of collisions, but there's even more subtypes than that. The two main subtypes we're going to focus on for the rest of this week are elastic collisions, where objects tend to bounce off from each other, and inelastic collisions, where the objects tend to stick together afterwards. Now, as said, momentum is always conserved in all types of collisions. So momentum doesn't really care what type of collision you have. The concept that cares what type of collision you have is actually kinetic energy. If you recall, the kinetic energy formula is 1/2 times mass times velocity squared. So if something has kinetic energy, that means it has mass and it is moving. Those same two variables are in the momentum formula, correct? Rho equals mv. Meaning that if you have kinetic energy, you also have momentum and vice versa. They're never the same number because it's different formulas, but they use the same concepts. So every single collision where momentum is involved, there is also kinetic energy present. That's true of everything, all of the collisions we've looked at this past week. The main difference between how momentum and how kinetic energy acts in a collision hinges again upon the fact that momentum only has one form, therefore it's always conserved as momentum, whereas kinetic energy is just a form of energy, meaning it can take lots of different forms. And the form that it takes depends on the type of collision you have. So the types of collisions don't actually affect the momentum that much. They affect what the kinetic energy that is also present is doing. To demonstrate this, I actually kind of want to go back to a previous example. This is the arrow and the log that we did on Friday. And we worked this one through with momentum. We looked at how, as the arrow approaches the log, the arrow has all the momentum. Upon impact, the two stick together. The arrow has to give most of its momentum to the log, and as they're stuck together, they now have a united final velocity that very slowly nudges the log forward. We did that by looking at conservation of momentum. I want to now go back to that and use the final velocity that we found to see what happens to the energy in that question. So real quick, I'm just going to redraw the arrow approaching the log. The arrow's initial speed is 25 meters per second, and its mass is 10 grams. The log's mass is 5 kilograms, and its initial speed is 0. After they collide, they end up, and please let me know if this is correct from your notes, they end up sharing a united final velocity of 0.05 meters per second. Is that correct? And when talking about momentum, we noted that the arrow initially had all the momentum. Once they collide, the arrow is going to share its momentum with the log. The same total amount exists, it's just dispersed differently between the both objects. And since they're stuck together, they now have one shared final velocity. We did all that with conservation of momentum, and now I want to instead look at conservation of kinetic energy. I want to see what happens to the kinetic energy in this scenario. To see if the total amount of kinetic energy present is the same from start to finish. So we're going to work this through like we did with momentum. We're just going to be looking at the kinetic energy of each object instead. And since both formulas rely on mass and velocity, we have all the information we need to find this stuff. Initially, which of the two objects has kinetic energy? The arrow. The arrow is the one that's moving. Momentum and kinetic energy are often paired with each other. So kinetic energy initial arrow plus kinetic energy initial log. This term is just going to end up being 0. And we will see if that is equal to the sum of their final energy levels. Note that I'm putting a question mark over the equal sign because we don't know if the two sides are equal yet. So now we'll just put in the kinetic energy formula instead of the momentum formula. On the initial side, we've got the arrow, 1/2 times the arrow's mass times its initial speed of 25. The log, its initial speed was 0, so it just doesn't have any kinetic energy to start with. On the final side, the masses stay the same, but each object has a different common final velocity, a very slow one. So the log has some kinetic energy, we just need to figure out how much. We already found the velocity from last time, so we're just going to use it to see what the log's energy level should be. On the initial side, the arrow's initial energy total should be about 3.125, and the log's is 0, because again, it wasn't moving yet. On the final side, the arrow's final energy level is 0.0000125, I think. Is that the right number of zeros?
I only get 2 zeros.
For the arrow?
So,
0.5, 0.01, 0.05 squared. I got 4 zeros for this one. I got 2 zeros on the log. The log should be 0.00625. Yeah, 625. Note that those are very small numbers. Nothing is very energetic after this crash. Keeping my question mark over the equal sign. On the left, that's going to leave our total at just the 3.125. Sorry, 3.125. And then on the right, those should add up to 0.0062625 joules. Are those two sides equal to each other? No, that's not a trick, and there's no way to make them equal to each other, because this type of collision is inelastic. The fact that the two sides do not equal each other, it doesn't mean the universe is broken. It means the universe is actually working correctly, because this was an inelastic collision. I'm usually very specific when I'm saying the word inelastic out loud, because I want to make it clear I'm not saying an elastic collision. This was an inelastic collision. It was not elastic. Anti-elastic, perfect. That is because the arrow didn't bounce off from the log, it stuck into it. They combined, and as a result of how they collided, kinetic energy was not conserved. There's a very big difference between the energy levels of the two sides. I think 99.5% of the kinetic energy is now just gone. Was it destroyed? Was the energy destroyed? No, good, correct. Energy can't be destroyed to our current understanding of physics. It just isn't kinetic anymore. So like 3.06 joules of kinetic energy is now likely heat inside of the log. And the way that works is when the arrow begins striking the log, before it begins embedding into the wood, the log exerts a force against the arrow, and that force acts as the arrow moves a distance into the wood. So force times distance, the wood does work on the arrow to take the arrow's energy away. And since that force, as the arrow buries itself into the log, is a frictional force, the bulk of that energy that the log takes away turns into heat, because friction always turns energy into heat. So the log does work to slow down the arrow. The arrow does work to deform the wood, because it makes that hole, it makes that dent that the arrow is now stuck in. That was energy spent up creating that hole. Now none of that energy is kinetic anymore. The only kinetic energy that's left is just the tiny little piece each object has to allow it to just slightly budge forward. And then that's going to immediately go away once it stops budging, once it goes back to rest. So by the end of this, all that kinetic energy is just gone. It's turned into something else. And that is true of all inelastic collisions, all anti-elastic collisions. You have an inelastic collision if the objects involved aren't elastic, so there's no rubber here, it's metal hitting wood, and if the objects tend to stick together afterwards. Whenever objects stick together, or at least stay together, travel together, that's usually a pretty good sign of an inelastic collision. And that's exactly what happened here. This is also true of car crashes. Frankly, most collisions tend to be inelastic, but car crashes especially are inelastic. And that's because car bumpers are designed from metal that isn't elastic. They crunch and then they stay crunched. If you've ever been in a fender bender, I know it's a pain to have to go get the bumper of your car fixed, but trust me, it's better than the alternative. Car crashes are designed to be inelastic, because if they were elastic, if car bumpers were, say, made of rubber that deforms and then goes back to normal, then the vehicles involved in the crash would spring off from each other as the bumpers go back to their normal shape, right? And if a car springs off from another car, not only does the person inside get worse whiplash because you've got a bigger change in velocity, you're likely going to spring off into oncoming traffic. So these are the signs of an inelastic collision. The objects stick together, they are not made of something like rubber or something that can bounce, and kinetic energy is not conserved. Energy is lost to things like friction and noise and heat and into doing the work of deforming the bumper of the vehicle, for example. For the wood, the work is done, there's energy spent up in the work of creating the hole in the wood. Now, in any given homework or test question, I will tell you what type of collision it is. You don't have to, I'm not going to make you guess that usually. I will tell you if something was elastic or inelastic. You just have to remember how to treat each of the two different types. For inelastic, again, when I tell you it's inelastic, KE initial does not equal KE final, and it tends to happen when objects stick together and are not made of elastic materials. Low energy, low impact. These collisions tend to be safer. They're more boring, but they're safer, and that's why car crashes are designed to be inelastic in nature. Does that sound all right so far? Okay. Now, elastic collisions are the inverse. Elastic collisions, you do maintain kinetic energy. And that's because in those crashes, the objects involved are elastic, and when they deform, they go back to normal. If this was elastic, that would mean that as the arrow digs a hole into the wood would fix itself and launch the arrow back out of the hole. Which doesn't happen here. But if they were made of elastic materials, that's why that would happen. And the energy does end up back in the kinetic state because when the objects collide and they temporarily warp from the impact, they go back to normal. They store the energy as EPE and then release it as KE again. So for an elastic collision, KE is conserved like how momentum is. And in an elastic collision, objects tend to bounce off from each other, usually at higher speed. Elastic collisions are more chaotic, more dangerous for that reason. Granted, most sports equipment is designed to collide elastically, noise ahead, because that's the only time in my life I've caught it after doing that. I will never repeat that feat. This is designed to collide elastically, specifically so that it bounces and so that the sport is more interesting. Questions so far? All right. Now, lab this week is about studying the two types of collisions. So if you've already had lab, I'm hoping this sounds familiar. If you haven't had lab, make sure to bring these notes. What we're going to do now is, technically most of the examples we've already done, other than the one literal cannonball, were inelastic collisions. I want to now begin at least, an elastic one so we can talk about the differences. And I've already said that car crashes are designed to be inelastic. I want to do an elastic car crash to prove why that's a bad idea. So we're going to cause a car crash. We're going to treat it like an elastic collision to demonstrate again why they are not meant to be that way. That said, for safety's sake, I've chosen two vehicles that can drive themselves. No humans are involved for legal reasons. So our two self-driving cars are Kit from Knight Rider, a self-driving talking sports car, and Nemesis Prime from Transformers, Optimus's evil twin. And these two vehicles are going to drive headlong at each other, and we're going to see what happens. Now, like all collisions, this is going to have a before state and an after state. So first up, our before state. All of my markers are dying. I still don't have a trash can to pitch them into. First up is our talking sports car. Mass of 400 kilograms, and it is driving forwards at 45 meters per second. I'm writing it first, so I'm just going to call that direction forwards. Next up is the truck. Mass of 2,000 kilograms, that's 5 times bigger. And its initial velocity is 45 meters per second in the opposite direction. Same magnitude, but opposite sign. We have to make one of them negative. And since I've drawn that one pointing to the left, I'm making the truck's velocity the negative number. So that's our initial state. These two vehicles are driving themselves straight at each other. And the after state kind of depends on the type of crash that we end up having. If this was a realistic, inelastic collision, what would happen is that the bumpers of the two vehicles would crunch. Most cars have a feature literally called a crumple zone. It's the zone of the car that crumples in the crash. And again, that deforms so that it absorbs all the energy and that the energy doesn't end up in your neck. What would realistically happen for an inelastic collision is the two vehicles would crunch against each other. The sports car would still be the one that's worse for wear. Most times the smaller vehicle tends to end up the most banged up one of the two. And realistically, they would eventually slowly come to a stop. Low energy, you want all the energy to go away, ideally in an inelastic collision. And they would be stuck together at the same final speed. And that's what we did with the arrow question. They stuck together, they combined, they had the same shared final velocity, and most of the energy went away. But we're going to make this elastic, just again, to demonstrate why we don't want to do that. So these two turbo cars have super elastic bumpers or something to that effect. And the weird thing that happens here is, since elastic objects tend to go back to normal and spring away from each other, noise ahead. Wow, that was the worst one yet. I am so sorry. Did I hit anything of yours?
No, it's fine.
Okay. I almost hit my own computer, which would have been real bad. Anyway, the only reason I did that was to point out again, elastic collisions, things bounce away from each other very chaotically and usually at different speeds in different directions. Which means that unlike when the arrow embeds itself in the log, we can no longer guarantee that these two vehicles will have the same final speed if we're treating it as an elastic collision. They would have two different final velocities until we prove that otherwise. So unlike with the arrow, where it was one VF in two different places, we cannot assume that is true here. And they would each have a different final velocity because odds are one of them is going to bounce away from each other at a bigger speed than the other. Guess which vehicle is probably going to spring away at a higher speed.
Sports car kid.
Sports car. Basically the same as when I throw a golf ball at the wall. The smaller object gets launched away faster because it has a smaller mass. It is easier to change its direction than the larger object. So, this is going to be a potential wrinkle for us, as I will soon demonstrate. Now, no matter what type of collision something is, we know total momentum initial is going to equal total momentum final. That is true of all collisions, of all interactions involving momentum. So no matter what else is going on, we can safely analyze the total momentum of this system to see what we can figure out from this equation. So, like with all the collisions so far, we're just going to compare the initial to the final. We have two different objects present in each side. So the left side would be momentum initial car plus momentum initial truck. And the right would be the sum of their finals. Same as the other collisions. On the initial side, we know both of their masses and both of their starting velocities, so we can completely solve the initial side, which is nice. Momentum initial car is going to be the car's mass times its initial speed. So 400 kilograms times 45 meters per second. The truck has a much bigger mass and is moving in the opposite direction. Both velocity and momentum are vectors, so we do care about that. So I have written negative 45 meters per second. This does actually mean, I want to solve the entire left side first to demonstrate this, that the left side will be a negative number. We're going to get a negative amount of total momentum. 400 times 45 is 18,000. 2,000 times negative 45 is negative 90,000. And so that means our initial momentum total is negative 72,000. Now the negative here doesn't mean anti-momentum, it just means the momentum points in the negative direction. So the total momentum of this entire system is leftward facing. This is bad news for the sports car. But does that make sense through to just the left side so far? All right. Now on the right side, this is where the problems start to manifest, because we don't know the final speed of either vehicle yet. We cannot guarantee that they're the same. We have to assume that they are very chaotically different.
We have their impulse.
So that would leave us with 400 times VF car plus 2,000 times VF truck, leaving us with one equation with two unknowns. Guess what comes next?
Equations with unknowns.
Exactly, everyone's favorite, right? We have to find a second equation with the same two unknown final velocities in it. Now, you guys are allowed to not like having to do this trick. However, I will point out that you don't have to, on your formula sheet, the equations you need are already written. Why is that here? Hold on. Your options for a second equation with the two unknowns are already laid out in your formula sheet. Because our momentum formula over there has been in terms of mass and velocity. And for an elastic collision, which is what we're treating this one as, the kinetic energies will also be conserved from start to finish. And kinetic energy also involves mass and velocity. So it would have the same unknowns in it. Meaning, we could use this as our second equation, analyzing the kinetic energy in tandem with the momentum. So you don't have to invent a second equation. One is already outlined for you. We just have to look at the kinetic energies instead of the momentums. Same basic process, but with 1/2 mv squared instead of mv. So to quickly demonstrate, for an elastic collision, kinetic energy initial equals kinetic energy final. KE initial car plus KE initial truck will equal KE final car plus KE final truck. And we just use 1/2 mv squared instead of mv. On the initial side, that would be 1/2 times 4,000 times 45 squared plus 1/2 times 2,000 times -45 squared. Note that that would actually cancel out the negative sign, because the negative number gets squared before we then do anything else with it. And that's because kinetic energy, like all forms of energy, is a scalar. It doesn't actually care what direction you're moving in, it just cares that you're moving. So whereas the momentum vectors over there end up negative, meaning leftwards, these will all be positive, just indicating that there is kinetic energy here. On the right side, 1/2 times the same masses times the unknown final velocities. The left side, we know everything here, so we can turn these just into known numbers. .5, 400, 45 squared. 405,000 plus 2,025,000. Takes a lot of energy to make a very heavy truck go fast. And then the right can't actually simplify all that much since we don't have either final velocity. This would just look something like 200 VF car squared plus 1,000 VF truck squared. On the left, we can combine that into a single number. On the right, we could distribute out a 200 if we wanted to, send it over, cancel it out, make all the numbers smaller. But ultimately, we have another equation with the same two unknowns in it. And that's the purpose this serves. Second equation, same two unknowns. We can combine them like we do, how we usually do with this trick. There is kind of a problem with that though, and it's the squared. Kinetic energy has a squared in it, right? And that means if we want to solve for either VF car or VF truck, we're going to end up needing to take the square root of a very big, ugly number. To kind of illustrate that point, I'm going to try to quickly show what that would look like. I simplify this as much as I can by just dividing out a 200 from this side just to make all the numbers smaller. That would end up being 12,150 equals VF car squared plus 5 times VF truck squared. So I just canceled out a 200 from everything. I added these two together, divided out a 200. I just like to do that to make the numbers smaller, saves time writing things. And to solve for, as an example, VF car, that would end up looking like VF car equals the square root of 12,150 minus 5 times VF truck squared. And that would be what we have to put into the other equation. Does that look like a pain? Does that fill you with dread? That is fair. I'm only drawing attention to it because there's a way around it. There's an alternative. I'm showing you this method because it does work. It is unfun, but it works, which is kind of the tagline for physics in general sometimes. You would have to take that over here, pop it in there, and have to work around that square root because we have to get that BF squared back out of it. It's possible, but not very fun. I'm drawing attention to it because we don't have to do it necessarily. Because it is true that this equation has the same two unknowns in it, but there's a third equation with the same two unknowns in it. It's this bottom one here that I haven't drawn attention to yet. This is a third equation for analyzing collisions. This equation only works for one-dimensional elastic collisions. So this is basically a replacement for this, for kinetic energy initial equals kinetic energy final. Because this only works for elastic. This doesn't work for the arrow in the log because that's inelastic. But if you're doing an elastic collision, and I will always tell you what type of collision it is, you don't have to guess. If you're doing an elastic collision, and as long as the objects are only colliding one-dimensionally, which just means forwards and backwards, equation 3 here is also a valid starting point like these other two are. And this contains the same two unknowns because it's just comparing the initial and final velocities of the two colliding objects. Velocity 1 initial minus velocity 2 initial equals velocity 2 final minus velocity 1 final. So as long as you've got two objects having a 1D elastic collision, that third equation can work in place of comparing the kinetic energies. And this has the same limitations because it came from this equation. Some very smart people studied this, simplified it down to this, so that you don't have to. Now, the way we would use this is we have to first pick which object is object 1 versus which object is object 2. I'm going to say that the car is number 1 and the truck is number 2. So if I was writing that out, if I was to use that formula, V initial car minus V initial truck. Note that we decided vehicle 1 was the car, vehicle 2 was the truck. On the other side, they switch positions. It's V2 final minus V1 final. So on the other side, it would be V final truck minus V final car. And this equation has the same two unknowns in it. And no squared. No squared or square root. We know the two initial velocities, and we're after these two. So it's one equation with the same two unknowns in it. Specifically, the car's velocity was 45 forwards, the truck's was 45 backwards. So it'd be 45 minus negative 45, which is just 90. So 90 equals VF truck minus VF car. Second equation, well, technically a third equation with the same two unknowns in it. And this, in my professional opinion, is a way easier thing to combine with this, because the squared is gone. So realistically, between all three of these, elastic equations have 3 starting points. And if you're analyzing the velocities, that means that you have 3 equations with the same 2 unknown final speeds in them. And you can pick any 2 of the 3. Namely, avoid this one because of the squared. Does that sound all right? Now, we're out of time today. I'm not going to hold you up. But like with all the other 2 equations or unknowns things, we would solve this for one of them, plug it into the other, We're going to eventually conclude this by noting the truck barely slows down, and the car is going to ricochet at like negative 115. But we'll finish that out next time. For right now, note again the difference between the two types. Your homework questions will tell you which type a collision is, so you don't have to guess. But which type it is affects which of these three things you can use for it. If you need anything, if you have any questions, on Friday we will practice this more and finish out Chapter 6. Bring all these notes to lab if you haven't had it yet. I'm rambling. Please have a nice day.